Everybody hear me? Hear me? Why did this stop? Strange. Okay. Can people hear and see me? I think if I try and record, it's blocking stuff. Anybody? That's all. Mic's off. Can nobody hear me? Oh, Lorenzo, you have a hand up, I believe. How do I accept these? You can also directly message in the side. There we go. Invite to speak. So you can come up and speak if you like, or you can send a message in there.
Yes, hello. We don't have permission for the chat. That's why we don't need to.
Sorry, your audio is very unclear for me. Could you repeat that?
Yeah, sorry. We don't have permission for the chat.
I'm
Yes.
really sorry. I really can't make out what you're saying. It's very muffled, the audio. You don't have access to the chat, you're saying?
Yes.
Oh, what the hell? How did that happen? You lost access to the chat. Oh God. They must have changed something about it, and I'm not sure I have the permissions to change that, and I'm not even sure where you do it. Because I think that's done by the administrator of PSE. Um, okay, so maybe this time around, I'm really sorry for this. I don't know what they've changed. Maybe this time around, if you want to ask a question, you can raise your hand, and I'll keep my eyes peeled for those. Yeah, then I'll make sure that's changed for next time, because that I know a lot of the time I don't want to speak when I ask a question. I just want to type one in the chat. So, I let me try and quickly send a message. Stick hands up. Maybe, yeah. Okay, so let's get going. Welcome to part 2. Same general points. There's the contents online, and this is where you'll start to see the order of stuff diverge. So I think polynomials, which is what we're going to do first now, is in the right place. But this the next stuff where we explore more generally what's happening will be at the end of the book. Stop me for any questions, as we said. If there's any quality issues, let me know, and I will do what I can to change that. Hopefully, there shouldn't be any audio issues. I think last time my VPN was turning on and off for some reason, and that was affecting the audio. Yeah. So in terms of the first session, I don't have any clarifications that I wanted to add. In terms of things that I should have expanded upon, but if you have any leftover questions from the first session, now is the best time to ask any of them. I'll just give you. Then I'll take that as no leftover questions. The first session was relatively straightforward, but I really think the main stuff you should definitely remember, regardless of what you do afterwards, because it'll probably be somewhat related to crypto. Remembering the stuff from the first lesson is the most important for just general understanding. And now we're going to do a bit more exploration of the space. So we can get going. So we're going to do three main things. Intro to polynomials, just a bit of maths, and that's going to help us understand some of the differences between the different proof systems. Ultimately, basically everything we're doing is related to polynomials, so it'll be a lot easier to discuss the differences if we look at them. I'm going to mention constraint count. That's really only 2-3 minutes. And then we're going to look at these different proof systems that are out there, only a few of them, because there are just tons and tons. Okay, a polynomial. I know it's a like sort of scary sounding maths word. Even I don't like it that much, but they're actually not that complicated. I'm sure all of you saw these in school, and it's just a function. F of x equals something. This one here we have 4xy squared plus 3x minus 5. And they're also limited in their shape. So I'll show you what I mean by quickly sketching. We can have f of x equals x cubed plus 4x plus 5. Now this is a polynomial, and the restrictions we have are that the powers, so this 3 here, and this x technically has a 1 there, we just don't write it because that's assumed what to be. The powers can only be whole numbers, and whole positive numbers, so x to the power 3, x to the power 5. We can't have a non-integer one, so x to the power 1.5, that's not allowed. Or g of x equals x to the 3 over 7, these aren't allowed. Similarly, the coefficient, the number in front, I mean, this is technically a 1, and this is a 5. These also have to be whole non-negative numbers. And that's the restriction we're working with. So they're fairly straightforward. And we also can't have a negative power, x to the minus 1, which is the same as 1 over x. Now, the example in the slide also has two terms. It has an x and a y. So if we're to write one of those, h of x comma y, we've got to put in both variables. We do x, y squared plus x squared y plus 5. This is also a polynomial. It fits our rules where we have the whole powers and the coefficients are fine as well. But for many of our proof systems, we won't work with two variables. We won't have a y. We'll only have an x. There are some proof systems that will work with multivariables, and they'll actually have tons of different variables. But for your initial learning, it's much easier to focus on single variable at a time, and this is what PLONK's going to do. Okay, so that's what a polynomial is, and you're going to see that we get a lot of properties very quickly. Now, the first thing we can do with polynomials, we can actually represent data inside our polynomials. And at first, that might sound a little confusing or strange, but it's actually really, really straightforward. And we're going to see the power very quickly. So I can do this through a little setting as well. Let's say that we're in a kind of online game show type thing, and we're guessing the price of some objects. And let's say I'm guessing that the first object is £37, and the next one is 51, and then it's 104. What I want is a way to prove to you later that this was my guess now, but I don't want to share my guess with you because then you know my stuff. I want to keep that secret. So what we can do, we can represent this data as a polynomial, and it's extremely straightforward. We're going to do f of x equals 37 plus 51x plus 104x squared, right? We just use them as coefficients. And you'll probably notice that we can just keep doing this. Like if I had more numbers going onwards, we could just keep adding higher powers of x. So we can stick as many numbers as we want in this polynomial. It could be 100, it could be 1,000, it could be in the millions. In practice, we'll be doing this with polynomials that contain millions of numbers as coefficients. So their powers of x go into the millions. So we can represent data inside the polynomial. But we're still stuck a little bit because, again, if I don't want to share my guess with you, sure, I might have a polynomial, but I don't want to share the polynomial because that still contains my data. So this is where we're going to get one of the scaling properties. We're just going to compress this, and I'm going to send you something called a commitment. I'm just going to evaluate this polynomial at a random number. We'll do f of different color. That's fine. F of I don't know. Let's do 10. Because this way I can work it out. 37 plus 51 times 10 plus 104 times 10 squared, which is going to give us 37 plus 510 plus 10,400, which is going to equal 10,947, I believe. And now I can send you this value. And if I give you this value, I evaluated it at 10 as well. So the value was polynomial was evaluated at 10, and that's the value, and that it contains three numbers. But you still can't actually work out what my coefficients were. Yeah? In this example, you might be able to brute force this because it's quite small, but in practice, we'll work with a much larger set. This random value won't be 10, it'll be some number in the millions, if not billions, or actually way higher than that. Right? So I can send you the commitment, and then later when I actually want to share my values, I will say, hey, my values were actually 37, 51, 104, and then you'll just make the polynomial yourselves, and you'll calculate it at this random point. And if you get the same value come out, your conclusion is going to be that was actually my polynomial. So we just did a lot right there. We represented data inside polynomials, and then we compressed it. Remember, these polynomials can contain millions, billions of data points, millions in practice. And we just represented all that data in a single number, this thing here that we called a commitment. And then I can later use that to prove the numbers I had earlier. Okay, so this is where a bunch of the scalability is coming from. It's by evaluating polynomials at random numbers. In practice, there's another cool thing I'll touch on, but we won't evaluate at 10. We'll evaluate at something called, we'll usually refer to it as tau. And what's interesting about tau is that it's a random number, but we don't actually know what the number is because it's an elliptic curve point. We haven't touched on any of this maths, but I'm just briefly mentioning it. But tau is actually an elliptic curve point, so we won't get out a number. We'll get out another elliptic curve point. And the interesting thing there is that we can actually keep reusing the same random value tau, even though we know sort of what tau, the elliptic curve point, is. Okay, so we'll touch more on that detail later, but the main point here is actually that we can get data and represent it in a polynomial. Yeah. So if you recall the image from the last session, we're going to add in a few more steps. We have the same starting point, value idea to idealized circuit. And then we're going to make the circuit, but now instead of going kind of straight to the polynomial, the proof, we're going to do a few things with the polynomial. And you can already guess some of it. The making of the polynomials, you just saw how we can do that, and I'll show you how we do it with a circuit. Then we do the committing to polynomials, and that was the evaluation at the random point. And then we'll do something called querying the polynomials, which is actually just evaluating it at another random point. Okay, and then you get out the proof. So how do we turn an actual circuit into a polynomial? Well, we're not going to make one polynomial. We're going to make a few of them. Okay, let's take circuit. That was a times plus plus. That's a multiply. Plus. That's a plus. And we have 3715. 3715. We can work out these values. They'll be, for a valid circuit, this will be 21. This will be 6, and this will be 27. So we'll make our first polynomial, and I'm going to call this L of x, because L is going to mean left. So we want the left wires, which is this wire here, and also this wire here. So that's 3 plus 1x. The 1 here is redundant, but I'm putting it in just for completion. And then plus 21x squared. Next, we want the next one, I'm going to call it R of x. And obviously, R is going to be right. So this is going to be this right wire, this right wire, this right wire. And that's it. So we have 7 plus 5x plus 6x squared. And lastly, we have O of x for out. And that's going to be this wire here, this wire here, and this wire here. So 21 plus 6x plus 27 x squared. We're representing some wire values more than once, twice. So for example, here, this 6 wire, we're representing it twice. And that's like done on purpose, because in practice, this isn't one wire. It is precisely, there we go. These are actually 2 separate wires. And what we're claiming is actually these 2 things are connected. So they're sort of the same wire, but that's actually because we connected them. And that's why it appears twice in our polynomials. And our proof system is going to confirm that these two wires or 2 gates are actually connected as we say they are. And then same as before, in fact, prior to that, you can now also see that we have this circuit, but we also sort of just represented it as polynomials. Like, are these the same thing? Like, sort of not, but also sort of yes. Like, they represent the same information as far as we're concerned. The polynomials don't actually don't fully demonstrate how gates are connected. That's one bit of information that's missing, and it is done by another polynomial, but we're just ignoring it for now because it's too much stuff at once, and we'll focus on some of what's happening. But you can see that this computation now presented physical gates being connected, but by polynomials. And regardless of the size of the computation, the number of gates, we can always make these polynomials. And then, as our outline showed, we can commit to them. So we're going to evaluate them at the random point, which is tau. So just do let's do this. To evaluate them at a random point. And then once I send you these values, these commitments, I've kind of locked in this circuit. Because if I want to change anything about it now, then I will change what this commitment value will be. And then you'll be able to notice that through the proof system. So this commitment is ensuring we kind of lock in place our circuit along with all the wire values. If you recall from last session, the wire values that aren't initially filled in are called the witness, and those are kind of private information for the prover. So we commit to them, and then what will happen afterwards is that we'll do something called querying, and essentially the verifier, you in this case, will come up with another random number, not tau, but a new random number. It can't be a number I was going to guess, because if I can guess it, I can cheat. So after I make these commitments, that's when you have to come up with the new random number. And there is a way to always do that. It's called the Fiat-Shamir. heuristic. I'm not going to go into how it works because take a few minutes and it's a tangent and not necessary. But after the commitments are sent, that's when we come up with a new random value, and then we'll get those values. Where's the red? L of, whoops. Yeah, that wasn't right. Of a new random value, or alpha. And then basically these values are the things that are going to go in the proof, and they should behave in a certain way that we're able to predict. Not going to show you how they should behave because that's several layers deep and several hours in of explaining the maths of how it all connects up. But these are going to be the things inside the proof. So I mean, we've been talking about proof in a very abstract way. We say there is this kind of object that is a proof. What it actually contains are these commitment values and these random queried values, and they're not actually like numbers like 3 or 10. They'll be elements of an elliptic curve. Okay, and then like I said, that will be our proof phi. Okay, so here's the new picture I just showed you in tandem with the previous one. So the top half is the previous one from last session, and the lower one is the new one with this additional info I just showed you. So if you recall, we started off and we'll have a value idea. Entrepreneur will say, let's build a circuit that creates a transaction or verifies a transaction or verifies a block in Ethereum, or that proves I can vote and allows somebody to vote, anything like that. We imagine what it sort of looks like, idealized circuit. Then we actually code it and turn it into a legit circuit with some values pre-filled out. And then anybody can use it. Let's say it's a voting one. It goes out to all of us, and we'll fill it in with our own values, our own secret keys to prove that we are the owners of it. We are the legitimate ID people, and that we're allowed to vote, and that we insert our vote as well. We'll take that filled out circuit, turn it into these polynomials. We'll commit to these polynomials, and then we'll be given random numbers to evaluate our polynomials at, and we'll do those evaluations. We'll combine those values into the proof, and then we'll send the proof. And then the tallying authority, whoever that's going to be, will receive all these proofs, check that they're all valid, and use them to build up the vote. Yeah, so that's the same process for any proof system. They basically all work with polynomials. They're all going to represent what's happening in polynomial. Some of them sort of don't necessarily look like polynomials, but they are still basically doing the same thing. And they'll make them, they'll then commit to them. They then want to kind of check it randomly, and then that's the proof, and it's sent off. Okay, so that's going to help us discuss, like I said, what some of the differences between different proof systems are, because it all comes down to how they work with polynomials. And then we have something called a constraint count, which is relevant to people working in this field because when we make our circuits, the voting circuit, how big is the circuit? How many gates are there? This circuit's got 3 gates, got a constraint count of 3. Very, very straightforward meaning. But the more gates you have, the larger the constraint count, the longer it takes to make a proof. And in some proof systems, also it means that the larger a proof is, the more points you've got to evaluate and stuff like that. So, all things being equal, you want to minimize the constraint count. Okay, so that was our touching on polynomials. We're now going to look at the different proof systems. I don't know if there's any questions about polynomials so far. to the next part. Yeah, this is an image taken from the online. We're just laying out a few different proof systems and doing a very high level comparison. The arithmetization, if you remember from last session, is how we turn our idealized circuit into an actual circuit. And for the PLONK and Halo 2, the second and third rows, it's called PLONKish. And that's what we've been drawing here. These addition and multiplication gates are PLONKish arithmetization. But Groth16 uses something called a rank 1 constraint system. And I'll just briefly sketch that. Instead of, yeah, it will have things of the form A1 plus A2 plus up to some value AK multiplied by B1 plus B2 plus up to another value B to M is going to equal another combination C1 plus C2 up to some value C. So it's not just addition and multiplication. Sometimes we say that addition is free, because if this is one constraint, you can keep adding things into the B part, B is 1. So you can sort of keep adding in new numbers into this single constraint, but you don't have to add more gates for it. You're just changing some of the stuff that's in there. And then you got to turn these into matrices, which are like the squares of numbers. And visually, this is a lot harder to work with. We can't draw pretty little addition and multiplication gates and connect them with wires. And then SNARKs usually use something called algebraic intermediate representation, and those look different again. Yeah, but you can look at the table on the online. We're just going to go through each system itself. Groth16 is unsurprisingly from 2016, and it was one of the first very good proof systems. There's been a lot of progress made since it came about, but it's still used in a variety of places. And the primary reason for that is it makes the smallest proofs. The proofs from Groth16 have only 3 objects inside them, 3 curve points, which is we know the theoretical minimum is more than 1, and it's an open question whether you can do it in 2 elements and not 3. But nothing is better than Groth16 as far as we're aware, unless it's changed very recently without my hearing of it. And also, because it's older, there's like a lot of stuff built around it. There's a lot of helpful stuff to learn how to use it, and a lot of libraries to use with it and stuff like that. So there's a lot of tooling, and the barrier to entry is a lot lower. So even though the prover time and stuff like that is not comparable to many of the newer systems, if you want to mega optimize the size of your proof, then this is still a great thing to go for. One of the main drawbacks about it, though, is it requires something called a trusted setup for every circuit. We haven't gone over what trusted setup is. I've mentioned it a couple of times, but it is a big security thing. So if you want to do it in an open, decentralized way, and if only 5 or 10 people take part, you just need one of these people to be honest in order for it to be safe. Now, if you have 5 or 10 people take part, you can question whether these people haven't actually colluded. Once you get, if 1,000 people take part, then you're going to be safe and secure. But that's very unlikely for it's just a single small circuit. So if you're going to be making lots of different circuits, you really don't want to be using R1CS. This is more for a single circuit used tons, maybe a transaction circuit or something else. Yeah, there's a bunch of circuits at the PSC that have been made with this that are still in use. Like I said, it's still in use in a variety of places. Then we come to PLONK, which is, like I said, is the main one we're kind of using for our structure of understanding. And if we get to when we get to it, a lot of the maths is related to how PLONK works. When I say it has a universal setup, This means it also has the trusted setup, the same as Groth16, but instead of having to do it for every single circuit, you do it once and you can use it with any circuit. And so then it's a lot easier to get 1,000 people to take part. And this has been done a bunch of times. There's a variety of them, and there's a way to update them as well. So that's a lot more versatile, and that helps the security a lot. And so PLONK has basically been developed and refined a variety of times. At the end, I'm going to just briefly mention some other proof systems rather than having their own slide. PLONK was a great innovation. I think 2019 is when it sort of came out, maybe 2020. I'm pretty sure 2019, and they just kept adding to it and making it better and better. But when we say PLONK, we kind of refer to the original paper. Vanilla PLONK is sometimes called. We have one called Halo 2, which is from the zkSNARKs or the Chain Electric Coin Company. It's something called a recursive proof system. So you don't just make a single proof. You actually it's kind of a chain of proofs. A proof is made, and then when you want to make another proof, let's say you want to prove the next vote. Instead of just proving the next vote, you'll actually take in the previous proof and sort of confirm that that was true and that your computation is also valid. And then the proof you get out doesn't just show that your vote was valid, but also that the previous one was valid. And you can build up this chain. I could try and sketch this. So in the voting example, if we do Groth16 or PLONK, we're going to have proof 1, proof 2, proof 3, proof 4. Oops. And we have to verify each of these single proofs. But in the case of a recursive proof system like Halo 2, we're going to do proof 1, and then this is going to go into proof 2. And then that resulting proof will go into proof 3. And then, of course, last into proof 4. And then the verifier only has to check proof 4, because that will confirm all of these and not just the last one. So you can see a lot of value there. In any kind of computation that requires a long-running thing, this is going to be ideal. A blockchain itself, the state, ultimately, that's what we want to do. We want to make a recursive proof of the entire history from the Genesis block, whether it was from 2014 or 2020. Ideally, that should be one proof rather than a proof for every single proof system. For every single block. I mean, you can imagine that you want to make a proof from the Genesis all the way to now. But if you want to do that as a single computation, that's going to be the billions, if not trillions and more values you have to put in your polynomials. And that's just going to be impossible, really, to make a proof for. It's going to be way, way too slow and take too long because the proof time is rarely linear, which it's actually super linear. So the larger it gets, it doesn't if the computation is twice as big, the proof generation time doesn't grow by a factor of 2, it grows by more than a factor of 2. So you can't just do a huge computation. You instead ideally want to do it in lots of little chunks, but keep combining these chunks together through a recursive proof system type thing. Halo 2 itself, it's also got a very high barrier to entry. It's very kind of tough to learn how to code with it. I tried to write an intro book thing, and it was very tough to understand. It does use the Plonkish arithmetization with the addition of multiplication gates. But yeah, it's tough to use. I think it's used at PSC a lot, although I think things have moved on a bit since Halo 2 because the new systems in the past couple of years have been very, very good. Then we move on to something called zkSTARKs. zkSTARKs are also a type of SNARK, but generally speaking, people might say STARK when they refer to a hash-based proof system, and SNARK when we refer to an elliptic curve-based proof system. They don't require a trusted setup ceremony, which is one of the positive security things about it that people like, because then you don't have to worry that they were colluding people and stuff like that. I think if you have 1,000 people take part in a trusted ceremony, it's fine. If it was done in an online decentralized way, if 1,000 people at Apple took part in their one, I'm not going to trust it. I'll be like, yo, that's just sketchy. But if it's done openly online and anybody can take part, I'm going to assume there's going to be at least one honest person. But they are also plausibly post-quantum secure. We add the word plausibly because we haven't proven that they're post-quantum secure, but we haven't found a way to break them with quantum computers. And this is we're not really expecting to. Maybe it's a little bit unfair to add the word plausibly because there's a variety of places in cryptography where we assume things. I might give you a quick overview because I think it's a very useful thing to know. But like in elliptic curves, we have a few hardness assumptions. There's something called the discrete uh, logarithm assumption, which we usually do dlog, which is why I capitalize them for short. And this basically says if you turn a number into an elliptic curve value, and give it to somebody else, they can't work out the original value. The only way they can do that is by brute force. There's no quick way to do it. And we don't have a proof that's the case. We don't have a proof that you have to brute force it. But no one's ever found a way to break it. So we believe it's hard. And, this has been known about for hundreds of years. So no one's figured out in that time. We think it's going to remain that way. But we do know 100% certain you can break discrete log with quantum computers. Yeah, we have an algorithm for that. So it's provably not quantum secure, but it's not proven to be normally secure. But the mounting evidence of nobody figuring out suggests it is. There's a few other elliptic curve type hardness assumptions. There's one for the type of cryptography that came before, which is called like RSA, and that's where you have two primes and multiply them together, and it's secure because people don't know the primes involved, which is called a hidden order group. That's the same thing. We're assuming that the only way to work out which two primes are multiplied together is to just brute force, essentially check all of them. And that's been known about for literally thousands of years, and we haven't found a fast way to do it. But we haven't proven that it's not possible yet either. But because there's thousands of years of evidence of humans failing, we're fairly confident that it's not possible, but we've just not figured out how to prove that it's not possible yet. And then for the STARKs, we work in something called the random oracle model. Oops. Oracle model. Which basically says that hash functions generate a properly random number. And we can't really prove that hash functions are definitely random, but we also haven't broken it yet either, and we also don't believe that quantum computers can break them. But so there's these hardness assumptions in different places, and different proof systems rely on different hardness assumptions. But that's where the post-quantum security discussion comes in. Generally, STARKs have been a lot slower than SNARKs or elliptic curve-based proof systems. So there is this tough trade-off, but at the same time, there have been some more recent developments that are speeding up STARKs in a way that SNARKs can't be sped up. So they're starting to combine elements of SNARKs and STARKs together to get the kind of optimal outcome. They use this different arithmetization that we discussed in air. But their proofs, unlike the several that came before, the proofs are not constant in size. You know, I say graph 16 has 3 elements in its proof. But for STARKs, the larger the computation, the larger the proof is. The larger the input size, which is the number of things you're filling out. Right. So that's a few trade-offs between some of these systems. But like I said, there's just the space is constantly changing. It's a very rapidly evolving area. There's a new one called Binius, which is trying to use like fields whose characteristic is 2, which is trying to minimize redundant computation. Like under normal circumstances, and this is actually what most of them are trying to do. But under the previous proof systems, because we don't treat 4 as the number 4, we treat it as like an element in a massive field, a 256-bit field. If you do like loads of index computation, you do 3 plus 7 and 5 minus 2, you're not actually working with a 2 or 3-bit number. You're working with the 256-bit number, and basically all of that is sort of redundant. Like it is there for security reasons, but there are other ways to find the security. Well, it's possible to have other ways to improve the security. So if you don't have to work with 256-bit numbers but can minimize it, you can minimize redundant computation and get lots of speed ups that way. And that's essentially what all of these sort of did. Asbinius working with like the binary hypercube. There's zkSNARKs, there's Plonky 2, which there was actually a Plonky 1. It's not like Plonk 2. There was a Plonky 1 originally from like Mir protocol, but I think they got bought out by Polygon. Then they made Plonky 2, and that was one of the first big innovations, and that was the reduction in size. Instead of using a 256-bit curve, I think they came down to like a 64-bit. And then Plonky 3 brought it down to a 32-bit, but they made up for the security loss by doing other things inside the protocol. And there's tons and tons of other systems as well. And each one of these, if you want to read the paper, it takes at least a week to kind of understand things in a bit with a bit more depth. So it's very hard to be an expert in all of these. Like ideally, you would have started 5 years ago and been doing it basically full time since. So don't worry if you don't know that many systems in detail. Like very, very few people do. And don't feel like that's a requirement to be a successful person in the space. You can be an expert in one of the popular currently used proof systems, and that's plenty sufficient. But of course, the more you do know, the better, and having a basic understanding of the differences between some of these proof systems will go a long way. But you don't have to know it, step-by-step detail. And that's kind of essentially it. I just had this little slide about what I do as a ZK engineer. I mentioned a bunch of this in the last session, so there's not too much to say there now. Like I'm focusing in a specific area about how we're trying to build at Terminal 3 where I work, we're trying to build a zero-knowledge database. So it's for kind of enterprises. So rather than any company have to look after all their user data, which means that every single company has to have their own kind of data team and with security engineers making sure that their data is secure and stuff like that. They can outsource essentially to us, and we'll make sure they're all safe because we can ensure that better rather than spreading the work amongst all of them. We can do it much more effectively, and we can also do it in a zero knowledge way to preserve the privacy of their users, and they can ask us a query and we will say, in this database, there are only 10 people who are female and living in Hong Kong with a master's earning over $100,000. But if they want to believe us, we have to make some form of proof. So we're finding ways to do that. But if we wanted to do it naively with the current proof systems, we've got to conduct a computation on a database that might have hundreds of thousands of entries, which is like huge, which would lead to constraint counts that are just way, way too big. So we've got to find ways to compress all of that. And in a similar way to how we saw that polynomials can be compressed and you can represent all the values in a single number, we can use tricks like that. So I've been looking at inside that about how we represent all that data, and then how we conduct like an intersection on the sets, or like, if the query is male and master, how do we get these two like subsets and combine them together and prove that the resulting set is actually, the proper query, and look at protocols for that, and a union as well, and then counting the number of people inside these polynomials. So for this, like, mine's more R&D. So I've been looking at different protocols, looking at the protocols that existed before, seeing if they work for us. If they don't, and seeing if we can improve them or find our own methods, and then coding it. And then there's discussion with the team. We've got to make a bunch of tests for the code. Gonna try and write a paper. So yeah, I mean, it varies month to month. Some months might be 60-70% coding and a few meetings and a few discussions. Some of it might be more 60-70% research. It's going to vary a lot when you're at a more early stage startup. Yeah, but that's probably the rough overview. Yeah. So, and also, like I said, I'm not working with actually a proof system per se right now. Like, we're trying to build our own SQL proof system, like a zkSQL proof system, which is the general proof systems work with arbitrary computation, which makes them very versatile but less ideal for specialized areas. And in our case, like I mentioned, a versatile proof system has proofs that are too big. So we're building a more specialized proof system. That's the end of this session. This is also a little bit short. I'm going to mention just a little homework thing afterwards for if you're curious. But the next two sessions are just going to be maths, only maths. So prepare a little bit. Hopefully you won't be too afraid. We're just going to briefly cover some of the main stuff that's involved, but we can't go into much detail. But ideally, by doing this, you'll understand a lot better the kinds of things you have to do and understand if you want to understand the proof systems in more detail, and that when you go to more advanced courses or look at more advanced material, you'll be better prepared. I'll just quickly do the homework stuff and ask if you have questions. I don't know how much you remember from Tuesday, but if you look at data and studies on this, yeah, going the wrong way around, but if you look at data and studies, this top left curve is called the forgetting curve. It turns out that like within 2 days, you usually forget like 60% of the stuff you learn. By 6-7 days later, you're down to like 10%. And it's kind of like, what's the point of learning if a week later you're left with basically nothing? Right? So that's really annoying. And so if you want to join an area, just going to single sessions isn't enough. You want to keep repeating this stuff. The top right curve is if you start to see this stuff again and again. I can't use a cursor to point at what I'm showing, but in the top right graph, the original learning line you'll see matches the curve to the left. But then once you see the material again, your first review, you'll see that the curve is much better, and that the bottom of the curve is a lot higher, so you'll retain more information. And then another review again will be even higher. And so I mean, this kind of is a little bit obvious. The more times you review material, the better you're gonna learn it. But at the same time, how many people go to lectures and things like that, and then review the material? Like, often we'll make notes, and the note-taking process is more effective for us to learn. But if we don't actually go and review the notes, we're still in the same scenario. Like, it might not be 10% that you remember a week later, maybe it's 15% because you encoded it a bit better. But you're still missing the most important thing, which is a review of this stuff. Yeah. And uh, so I'm going to mention like something I've changed in how I learn stuff in the past year, and it's been like phenomenal. And I wish I did this a long time ago. And it's based on like really, really solid, heavy science stuff, and it's like very obvious to that it works super well, but we haven't done stuff this way. At the top right, we're showing that if you see the material again, if you review it, you're going to learn it better. So there's a thing called a spaced repetition system. On the left, I put SRS emphasis. This is a spaced repetition system. And what it is, they're just actually flashcards, basically. And there's an algorithm. So you'll see the flashcard, you'll see the front, you'll try and remember the back, and then you'll kind of score. When you look at the back, you'll score it from 1 to 4 on how well you remembered it. And then there's an algorithm that determines when to show you it again. And these algorithms are scientifically optimized to be as efficient as possible at getting small bits of data into your long-term memory. So at first it will show it to you 3 days later, and then 5, and then a week, and then 2 weeks, and then a month, and then 6 months. Something like that, depending on how well you remembered the back when you saw the front. So that time delay extends out pretty quickly, and then within a few reviews, it'll be a year or 2 years before you have to see it again. And these bottom graphs, this is data from this kind of thing. So the leftmost one, obviously the color coding, the red is when you receive material and just study it. The yellow is when you receive material and you personally study it a few more times. The blue one is concept mapping. So you receive the material and then you concept map, and this is where you kind of mind map. You'll draw like that'd be easier if I just think like polynomial, and then you do like a field. You're kind of mind mapping this all together. And then you have retrieval practice, which is the flashcards I mentioned, because when you see the front of a flashcard, the thing your brain actually has to do is you have to retrieve the information that you know is going to be back. Like based on the front, what do you have? What memory do you have to retrieve? So it's referred to as retrieval practice, and it's done via this kind of spaced repetition system. And in this study, with verbatim questions, and verbatim means like word for word. If it's like what is this equation? You want a very specific answer. It's not open to interpretation. It's just like what was this definition, or something like that. And you'll see that the proportion they got correct, the best group by far was the spaced repetition system, this retrieval practice. Okay, and then we move to the inference questions. And this is where the inference question is where the answer wasn't like given directly, but it has to be inferred from the information that was there. So maybe it asks for like the volume of a bottle, and you were given the equation for a shape, bottle shape, and then you have to kind of work it out. Anything like that, where you have to use the information you got to figure out what the correct answer to the other thing should be. And even here, you can see there's a kind of like still a very clear gap for the retrieval practice. It's not as big as it was before, but it's still better. And then what I find very interesting is this last graph called metacognitive predictions, which is a very strange term, but all it actually means is they asked people which method they thought would do the best. And people thought repeated study was going to do the best, probably because it's what we all do at school. And they also thought retrieval practice was going to do the worst. And the most insane thing to me about that is that the retrieval practice is the study plus the retrieval practice. And yet they thought it would do worse than just study on its own. So not only is this like the best way to learn, there seemed to be some kind of misconception. I don't know if this has been this information for this last graph in particular has been recreated elsewhere, but the best method is thought to be the worst method. Okay, so that's my spiel about memory and trying to remember this stuff. And if you want to join the field, particularly if you're like kind of doing this part-time, if you watch a lecture this week and two, and the next week a little bit, it's very hard to hit the kind of critical mass of time spent with the material to not need something like this, a method to go over the material again. So that's why I'm recommending this. And I use this for all my stuff. I learn all my cryptography and anything else I read. Because if I read an article or like 5 or 10 articles about how a blockchain works and not cryptography, which is what I actually focus on, 2-3 months later, I've totally forgotten these articles. Don't remember anything from them. And that's happened again and again and again, where I've learned some stuff from other fields, but I haven't reviewed it because who actually reviews it? And I've forgotten that stuff. But now instead, I get this information. Instead of like note taking, I will make my flashcards, and then I'll keep going over them. So whenever I do read something and I make a flashcard about it, I will still know it, generally speaking, 6 months later, a year later. So what this system is, it's called Anki. It's free, you can download it for free. And here's an example of a flashcard that I've made. I said, like, what is the gas cost of verifying a PLONK proof versus a Starkware proof on Ethereum? And on the back, the thing I have to try and remember is it's under 300,000 gas for PLONK and around 5 million for Starkware. Some of that might have changed a little bit because it's a new proof system that Starkware might use. Yeah, I'm going to even show you quickly. Yeah, here's my Anki. I can just go to all my cards I've got new, and here's all it is. What are zkSNARKs? I made this today. I didn't actually remember it very well. I mean, like I said, I wrote it this morning. The size of the proofs. Sorry, the size of the proof system. The arithmetic fields we're working in to get speed ups. New start construction that somehow makes use of points on the unit circle. Oh yeah. Sorry, that's what the circle part's for. We're somehow making use of things on the unit circle. So I haven't really read into zkSNARKs much at all yet. But because of this card, I will now sort of remember the rough overview of like the point of them. And then on the bottom, you can see the difficulty thing. See it in 1 minute or 10 minutes or 1 day or 5 days. I'm going to do 10 minutes. What is a data race? This is for, to get better at programming. And this is where you have undefined behavior because things aren't going to access data in a predetermined order. It's going to be some kind of randomness there. So undefined behavior, and I remember that more verbatim because I have this card. And I will just I will use this several days a week and go over all the knowledge I have. So it's very easy to use. There's so much data about how it's going to help you. So I would super recommend it. And of course, the homework would be go and make some slides on things you want to remember. One useful heuristic is you can try and set like a quota or something. So if you go to a lecture, try and make 3 or 5 or 10 cards. If you read an article, try and make 2 or 3 cards, and you force yourself to make a certain number of cards when you do stuff. So you've set yourself a habit. Maybe also like encapsulation ones, like say what a zkSNARK is in one sentence is a nice one because you're instead of like end up writing loads, which isn't actually what you should be doing. You're trying to get your brain to encapsulate all the information into a single sentence. So there's a lot of stuff there about what cards you actually and how you represent it. That will determine what you actually remember, which is something you'll learn as you go. But anyway, end of my spiel. The point is, there's if you are interested, download Anki, free open source software, and start to make cards to help you learn this stuff much more effectively. And the gains from this will just kind of accumulate over time. Yeah, cool. So any questions about anything said today or last session? Maybe you can also message me personally, and I can open the question on this. If you don't want to speak on stage, on my Lost in the Witness account. No questions yet. So I don't know. If you message me, I don't necessarily know where it will message me. Don't know if that's a question. No, on this account. Right. Okay. Are those questions? Message request. Do have one question, but it's from 30 minutes ago. Okay, no questions yet. Okay, it's not a question. Yeah, sorry about this side chat issue. I I imagine because I asked them about the ability to raise your hand, and I guess they disabled it by accident or something, which is very unfortunate. Um, but we'll fix that 100% for next session because that really sucks. I like when I'm in these sessions, I don't want to come on stage. I just want to ask in the side chat. So someone is, I believe, typing a question. But do recall that the next sessions will be the same time on the same days next week, so Tuesday and Thursday, at the same time we started. But those are just going to be maths. Yeah, that's all we're going to focus on. So I'm having a question. Halo 2 recursive proofs can be chained on the proof of the same circuits. Yeah. There's something I don't fully recall right now, actually, but that's a good point. When I was just showing Halo, this recursive proof system where you're chucking in, one proof into the next proof, does the circuit have to be the same circuit as the one you're proving? Like, if it's a voting circuit, can you then chuck in a transaction circuit and prove that as well? For Halo, I can't fully remember. There's other systems called they're referred to as folding systems, and something like Halo sorry, not Halo, Nova and Hypernova. In those ones, the circuit has to be the same. If it's a voting circuit, the other one has to be the exact same circuit. You can't have any changes. But in Halo 2, I can't fully remember. I believe the answer is yes, but I can't say that definitively. So there's still some restriction in the ability to recursively prove stuff. But yeah, there's a not proof system, blockchain called Mina, and they use a recursive proof system. I think it was Kimchi or something that they made themselves to recursively prove their entire blockchain, and it was designed like that from the beginning. So they claim to be the kind of smallest blockchain because it's like less than a megabyte or something, and that's because they keep updating their proof of their blockchain. So you can see the state of their blockchain and confirm it in a fraction of a second because it's just a single block with a single proof. Because the proof demonstrates that everything that came before is also valid. But yeah, pretty sure Halo 2, you have to do it on the same circuit if you're recursing it. Cool. No other questions. So I'm gonna assume there aren't any more, unless someone has their hand up, which I don't think they do. Cool. Well, thank you, everybody. Nice to see you all again. Hopefully we get the recording for this session as well. Oh, yeah, about the previous recording. I believe Hangliang's still working on it. As soon as I get the link, we can share it, unless it's already been shared. Yeah, so I will chat with Hangliang about the last recording, and we'll try and get this recording out as well. Thank you. Have a good week. Please do check out Anki. I sincerely recommend it to help your general learning. And we'll go over the maths on Tuesday. Ask me any questions whenever you please. Bye. Take care. Have a good, I'm assuming, evening. I believe most people are in Asia. Okay. Bye-bye.